So we're going to look at composite functions. So a function that is a composition of other functions. So say we've got this set of numbers. These are our x values, just simply 1, 2, 3, 4, 5. And we apply the function 2x plus 1. Then 1 would go to 3, 2 would go to 5, 3 would go to 7, 4 would go to 9, 5 would go to 11. So any x value would go to 2x plus 1. But then we go and apply another function to this set. So let's say we apply 3x squared to everything in the second set. So 3 will go to 27, 5 will go to 75, 7 will go to 147, 9 will go to 243, 11 will go to 363. Well, that would be equivalent to if I just got the first set and applied a function to it to get the third set. The question is, what is that function? Well, it's the one we would get if we substituted in 3x squared into function x. And on this one, it actually turns out to be 12x squared plus 12x plus 3. So it's the composite function. It's the equivalent of putting x into one function and then into another one. There's our notation for it, because we're saying it's the g of function x. We've substituted function x into g. If you did it the other way round, normally you will get different ones. It's very rare you would get the same function. So if I was to substitute gx into function x, so now I'm substituting 3x squared into function x, then we actually end up with 6x squared plus 1. So two different functions, both quadratics, but other than that, there's no other similarity. All right, so how do we find the domain and range of these composite functions? If you want to find the value of the domain of the composite function, two things you need to consider. First thing, if I'm substituting gx into f, then x must be in the domain of gx. So remember, first of all, we've got to get the x, substitute it into the g. Now, if I can't do that, if it's not in the domain of g, then I can't go and then substitute the answer in the function x. So we've got to look at the domain of what we're substituting into. But then the answer, so when you substitute in, you get an answer for g of x. That answer must be in the domain of function x. Because if it's not in the domain, then I can't substitute that answer into the function. So there's two things to look at. Now, with the range, a value of function gx, so your final answer, is in the range of the composite function only if the x value that you substituted in originally is in the domain of function gx. Let's look at some examples, see if this makes sense. Here's my two functions. Function x is going to be 2x on 4 minus x. G of x is 1 on x squared. So find the domain and range. Well, I'm just going to look at each function individually and work out the domain and range for those. So 1 on x squared, I know my domain's fine, I just can't substitute 0 into that one. Can't have 0 on the bottom of a fraction. Its range, well, that one's always going to be positive, isn't it? Because I've got 1 divided by a squared number, so there's no way I could get a negative number for that. And of course I can't get the answer 0 because of the constant on the top of the fraction. So g of x will always be greater than 0. Now the other function, 2x on 4 minus x. Well, that one in the domain, I can't get 4. So it's the real numbers excluding 4. The range on that one, turns out you can't get negative 2. If you were to do a polynomial division on that fraction, you'll see it ends up being negative 2 plus some constant number on 4 minus x. So you couldn't end up with negative 2. All right, so I need that bit of information first. We said x must be in the domain of gx, because that's what we're substituting in. So if we go back to gx, we said, oh, it's all real numbers except 0. So straight away I know 0 can't be in the domain of the composite function because of that. So x can't equal 0. The other condition, the answers must be in the domain of function x. The other condition, the answers must be in the domain of function x. So the answers, the range, but it can't equal 4. Because we said g of x can't equal 4. Go back to our domain. I can substitute in anything, but I can't substitute in 4. So g of x can't equal 4. That means 1 on x squared can't equal 4. So now I get two other exclusions. X can't equal 1 on 2. So there's my domain of the composite function. Can't be 0, can't be plus or minus a half. Now the range, this is what we said. A value for the composite function, so whatever the answer is going to be, is in the range only if the x value that gets that answer is in the domain. I think it's easier just to work out what the actual composite function is and have a look at that. So if I substitute in 1 on x squared, I end up with 2 over 4x squared minus 1. And I think it's just easier to look at that and go, well, what is the range of that function? So the range of that function itself is, now it's tempting to write y is less than or equal to minus 2, but I don't, because it's representing two different things. Remember, we had y equals function x, we had y equals g of x. So which y am I talking about? So I'm highlighting here, no, I'm talking about the answers when we substitute g of x into f. So function g of x would be less than or equal to minus 2, but also greater than 0. So it'll be the union of those two sets. But remember, we said x can't equal 0. So it means I can't substitute 0 into this. Well, that gets the answer negative 2. Well, that affects what I thought the range was. Just slightly, because I thought the range was going to be less than or equal to negative 2, but I can't actually get negative 2. So the range just turns out to be less than negative 2 and greater than 0. So the range, so I think it's just easier to look at what the actual answer is and work out the range, disregarding everything else, what the range would be, then going to have a look at what did you restrict in the domain to see if there's any other answers you have to exclude. Let's go back the other way. Let's put function x into g of x. Right? X must be in the domain, this time it must be in the domain of function x, because we're substituting function x in, and that was x can't equal 4. Every other value was fine. X can't equal 4. But then we also said function x, so the answer that we get out must be in the domain of g of x. So function x in our one can't equal 0. So 2x on 4 minus x can't equal 0. Well, that means x can't equal 0. We actually end up with the same domain this time. Can't equal 0 or 4. Then the range is the tricky one. The value of g of function x is in the range only if x is in the domain of g of function x. Okay, so we've worked out the domain of g of function x. Let's work out the actual function. In this time, when I substitute in 2x on 4 minus x, we end up with this, 4 minus x squared over 4x squared. Now, for that one, its range, again, it's one of these ones where, hang on, this is always going to be positive because we've got squares. So that would be that actual function. But hang on a sec, we said, back up there, you'll see we said x can't equal 4. Well, what do we get if we did substitute in 4? We'd get the answer 0. Well, that means I can't produce the answer 0. So it has to be excluded from the range of our composite function. So it now becomes just greater than 0. Just in the box here, I've just put down something very strange. If the domain is the empty set, now think about that, the domain is the empty set. That means there's no numbers in the domain whatsoever. So you've got this function where it's impossible to substitute anything into it. What? How can you have a function that's impossible? Well, you can't really write down the function, but it's known as the empty function because there's nothing there. You can't substitute in because there's nothing there. It's empty. It's just a formal little definition, though. All right, we shall do. Excellent. You know what we're up to? Exercise, jolly good fellow.